Welcome to the third episode in a series where I'm providing some updated information for my DIY PCB tutorial. So before we get into the precision part of the air assist discussion, let's talk about air assist itself first. Actually, my laser didn't even come with an air assist nozzle, but in an effort to try and get some active cooling when I'm clearing the pads, I machined up one myself, which works pretty well for that purpose. But my original testing with the nozzle didn't really seem to add much benefit for other PCB related processes. So basically I thought the usage scope would be pretty limited. But as has happened so many times before, I was completely wrong. And it turns out that air assist can play a pretty critical role for various different operations in my PCB manufacturing process. So I don't really want to bore you with a long story about all of the discovery process. So let's just cut to the chase about what air assist actually brings to the table in this PCB process. And actually it's a lot more than you might really expect. I think the one that most people are aware of is for minimizing surface staining. So surface staining often happens when you burn a surface like wood, but by actively blowing away the garbage in the smoke, it actually stops it from settling back down and onto and into the surface, and generally you get a cleaner finish, right? However, this is not really a factor for the materials that I use when I'm making PCBs, as any residue can usually simply be wiped straight off. So the next one is smoke control, or in other words, getting the smoke out of the path of the laser so that the power is not degraded and remains consistent throughout the job. Now this one is actually important enough for PCB making, as we need constant and predictable power levels getting to the surface of the work. But even so, in my experience, it's sort of pretty hard to judge how much of a factor that actually is. But I guess you could say that making it no factor is better than being a possible factor. So yeah, I think it's probably beneficial in that regards. And next we have keeping the laser's lens clean, which through hard experience I've actually learned is really very important. If you're not using air assist, then what will happen is the residue from the smoke etc. will rise up and over time build up a layer of gunk on your laser's lens. Now honestly I thought this wouldn't really matter much, and when I was starting to get very inconsistent results for given power settings, typically meaning that I would need to gradually increase the power level, I actually thought this was just a feature of the laser aging with use. But then, all of a sudden, things were starting to get too hot with the new settings that I was using, and I then had to go ahead and reduce the power levels. So it had me pretty perplexed, and I was suspecting all sort of things like the obviously instability in the laser itself, instability in the power supply, or some sort of instability in the control signal. But then I realized that the power boost was seen always just after I'd cleaned the lens. So there I had finally found the smoking gun. Yes, pun intended. And in hindsight, it should have been pretty obvious. I mean, I've seen a number of lasers on sale on AliExpress where they specifically show in their write-up that you should not touch and leave fingerprints on the lens. And clearly they are saying this for a reason. So naturally, if just fingerprints are going to negatively affect the laser's performance, then obviously a layer of smoky residue gunk is going to be much worse, and it obviously is. Even just keeping a tiny bit of positive pressure in your air assist nozzle when burning something will keep the smoke out, and it's going to keep your lens clean, and that's going to give you a much more consistent result in the long term. And the final benefit of air assist is the original one that I actually started using it for, and that is active cooling. And it sort of turns out there are somewhat two different objectives you are probably going to be seeking to achieve when you're trying to use active cooling. The first is to cool the general area that the burning is occurring. For example, too much heat buildup within a localized area can actually cause, say, your UV resin coat to lift off. And when clearing the etch resist layer, this can actually be a problem with some types of design that require a lot of burning in a localized area, and it's actually something that I've experienced myself. And even though the unetched copper board has a huge ability to sink and transmit the heat around the surface, it still has a limit. Some light active cooling can just be enough to stop the board from getting to that critical heating point. Now, it's something that I've also gone over many times as well, but when you're clearing the pads, you also run the risk of overheating in a localized area. And this is specifically problematic for very tiny pads that usually have a very limited ability to sink or distribute the heat over a wider area. And if uncooled, there are even cases where the copper pad will heat red hot, which burns the substrate of the PCB, causing the pad to actually detach from the surface of the PCB, which is clearly not a desirable outcome. Now I will mention here with a little spoiler that I'm going to actually show some new strategies in an upcoming video that will greatly reduce the amount of heating that we get on these types of smaller pads. But even with these strategies, it still requires some pretty aggressive air assist to keep things cool. So the second type of cooling objective is something that I tell myself is something like putting out the fire. And it's sort of joking there, but it's also not really joking too. Obviously, it's going to depend on the material that you're working with, but some materials will actually build up a heat front as you continue to burn. And this can actually cause a wider burn that you would actually like. So as you can see, that's quite a different problem to the localized area. You're actually getting an effect to the burn pattern. Now, I found that materials like vellum are particularly sensitive to this. Vellum can be really, really hard to get a burn to initiate, for example. But once it starts burning, it just builds up that heat. It gets hotter and hotter, and the burn gets more aggressive and aggressive. And that's especially the case if the burn is in a very, very localized area where you're really concentrating the heat. So just using a little bit of active cooling actually tamps down the burn a little bit, and it can actually give you a really, really nice result. And all of this is actually a bit funny when you think about it. I mean, we're using the air assist to get the smoke out of the way so that we can then transmit more heat into the work. And then we're using the air assist to play a role in getting the heat out of the work as quickly as possible, or in a controlled fashion as possible. I think it's also intuitively difficult to understand why that blowing more air into something that's actively burning does not actually exacerbate the burning. But my experience shows that it clearly does the exact opposite. Now, I can only conclude that the cooling effect of the area is much more a factor than the additional oxygen that we're pumping in there, right? Anyway, enough of the waffle. I think you get it. Air assist is actually pretty damn important. So if you don't have it, then I recommend you go out and get it. So that should be the end of the story, right? Well, it's clearly not, since we're still only probably less than halfway into this video. So anyway, my air assist is working well, but there are some things that I'm just really not happy with. In particular, I struggle with the lack of the ability to precisely control the amount of air that's being delivered with my setup. And everything about my PCB process when I'm actually using a laser, it's really all about precise and consistent control of the heating levels. And if I cannot always deliver that exact same amount of air for a given operation, of course, this is going to give varying results. And this is all made a lot worse by the rather oversized and inappropriate air compressor that I'm using in my setup, where it's basically impossible to set a precise air pressure level, given the pressure scale it uses is actually nearly 20 times larger than the maximum amount of air that I would ever need for air assist. So say in the case where I just want to keep a positive amount of air pressure in the nozzle just to keep the smoke out, well, it's basically impossible to precisely set such a low amount of air pressure with my current compressor's regulator. I've even found that sometimes it can stop sending any air after a little while when I'm using such low settings. And as something that I would probably say a little bit of a side concern, I also don't want to have my air compressor to work any harder than it absolutely needs to, both because it's noisy, but also because it causes unnecessary wear and tear on what is actually a pretty expensive little air compressor. I want to have the ability to regulate the air pressure in a much lower pressure range, and of course I need to be able to set and confirm exactly what air pressure is being sent to my nozzle. Now, I guess buying a dedicated air assist unit or even buying a cheap air compressor operating in a lower pressure range could be a solution, but I just don't know. But I somewhat doubt it would be able to provide the degree of precision that I'm looking for in any case. And obviously there's the other fact that I'm a bit of a cheap ass and I don't want to go and spend more money on buying another device because I've already got something that somewhat works. So instead, I decided to try to build my own precision, electronically controlled low pressure air regulator. And this is one of those projects where I really thought that failure was not only an option, but it was more so a likelihood given my total lack of knowledge in any of this stuff. So the first thing I did was to study up a little bit on how normal air regulators actually work. And it turns out that most of them seem to work by having an input side and output side pressure chamber with some sort of separating diaphragm, which is pressed by an adjustable spring, which in turn is what regulates the pressure. So the simple way to think of it is that if there's a differential pressure between the chambers that is strong enough to overcome the pressure that the spring is applying to the diaphragm, then air is going to pass until the equilibrium is met and the diaphragm closes down again. Anyway, something like that. It's not really the point of this video. So I think my original idea was coming up with some sort of electronically actuated version of something like that. But as you can hear by that discussion that I've just had, it actually seemed a little bit more complicated and a little bit beyond what I'm sort of comfortable with, if I'm quite honest. So I tried to think about doing something a little bit simpler, and the first thing I sort of sat down and drew up was the idea of simply crushing the silicon air pipe to try to restrict the airflow, and then having a small pressure chamber on the upper side where I could measure the pressure and then have some sort of feedback loop to try and control that valve. But it started to become pretty apparent that trying to crush that pipe in a reliably controlled fashion, it was not going to be an easy thing to do. I mean, think about this. Have you ever tried to stop water that is already flowing through a water hose just simply by crushing it with your fingertips? As you very well likely know, it's nearly impossible to do. So even though this is only using air, and obviously it's going to be at a much smaller scale, using this approach is still going to be a pretty hard thing to implement. But actually it's interesting because, trying to understand those forces and how I might be able to control them and coming up with that analog of using a water hose actually led me to what is a pretty obvious solution in hindsight. And I'm pretty sure that most of you already know the answer to this problem at this point of the discussion. Yep, that's right. Folding back a water hose on itself actually requires very little effort to stop water flow. And there's even some reasonable level of controllability that can be had too. I even went ahead and did a few tests with air flowing through a silicone pipe, which I then folded and saw how I controlled the air. And the results actually looked pretty promising, though I was not really sure about how accurate or what sort of range of control I might get. But there was enough there to make me move forward and try to come up with a more implementable design. So to help control the fold point of the silicone pipe, I installed some aluminium pipes into the silicone hose, and I sort of restrained everything with some 3D printed clamps. And then to get the folding action, I actually have one side of those clamps connected to an articulating arm, which is attached to a small servo. And as that servo rotates around, it either folds or unfolds the silicone pipe to a varying degree. It's actually really, really simple. Obviously, I still needed the chamber to measure the air pressure on the output side, but I thought it might also be a good idea to have a bit of a buffer, something that actually damped down any sharp changes in air pressure. And I was thinking that that would be something that would make the sensor measurement and the airflow to the nozzle a little bit more stable. So originally I was actually thinking about using some sort of 3D printed chamber, but actually in the end it sort of occurred to me that I could use a PET drink bottle. So I ended up using a 600 milliliter PET drink bottle, and I installed the pressure sensor, and obviously I have an air input pipe and an air output pipe. And all of this is sort of held in place with some hot glue, which I've sort of liberally applied to both sides actually, and that seems to work quite well. I did also take care to stagger the heights of all of these elements, and interestingly enough, the PET bottle actually has a little bit more elasticity than I thought it might have had, and at the higher pressure settings, I can really feel it balloon up in diameter a bit. So anyway, I'm pretty sure the PET bottle is actually acting as a bit of a damper like I had hoped, though I didn't really do any experimentation to confirm what sizes of bottle might provide more or less damping effect. But what I can confirm is that the pressure measurements that I am getting are very stable, yet reactive enough to allow me to dynamically adjust the valve. So in this regards, this configuration I think is actually a valid one and working quite well. Now I don't want to focus too much on the controller I use. Honestly, what this thing is doing is really, really very super basic, so pretty much any sort of microcontroller is going to do the job. So this controller with the screen and buttons is just one that I had left over from my original drum pedal controller that I made. I'm also using the AS5600 knob and the related class that I showed in a prior video. And this is the first time that I've actually used this in a practical project. And it works pretty damn nicely. I'm very satisfied with the way it functions. And it's easy enough to simply twist the knob to set to the desired pressure level. And I actually use the press button feature of the knob to start and stop it. I also linked in this reed switch to the same button, and I mounted it so it's on the X gantry. That means that when the job's finished, I just move the Z axis assembly all the way to the far left, and that triggers the little reed switch and it turns off the air automatically. I've also got it set up so that it emits a rather annoying, but at the same time very useful, sort of continuous beeping sound until you come back and move the axis out of the way. The code itself is nothing special. I've just based it on the vanilla Arduino PID controller. That's actually the first time I've actually finally got the PID controller to work, which is a little bit embarrassing, but in any case, that's the truth. Anyway, it takes the pressure level from the sensor, and then it controls the servo to try to maintain the level that is set by the knob here. Now I'm going to provide a little bit more information in the description or in the pinned comments or a combination of that. So hopefully that's going to make it easy enough for someone who wants to make one of these. I'll also provide all the 3D printed files on Printable as usual, so if you want to make that, go ahead, knock yourself out. Now I really don't know if this is going to work in combination with an off-the-shelf air assist product. I guess it might, but honestly I do have my doubts. But I'm pretty sure it's going to work with most compressors that had some type of regulated output, even ones that cost as cheap as say $100 US. But I would probably recommend a couple of things to keep in mind if you're going to go out and buy one. First, you want to make sure you get one that pumps as many liters of air per minute as possible for whatever budget you have available. The most amount of air that you can generate is really going to limit the amount of maximum sort of air pressure that you're going to output on the output side. And probably a second level priority would be to try and get the largest possible air tank you can get on your compressor. The larger the air tank is, the less frequently the air compressor is going to need to operate. And obviously that's going to increase the level of serenity in your workshop. Anyway, do your research and try to get something somewhat decent, because these are the sort of things you really should be or want to be buying once. You don't want to go back and buy it again. And really the great thing about buying an air compressor is that they are really super useful for all sorts of stuff. So you really can't go wrong with buying one. Anyway, let's do a little demonstration so you can get some idea of how well this precision air assist regulator actually works. So for this demonstration, I've got the cover off so you can see what's going on. So let's do it that way. Obviously, normally you'd want the cover on so you don't get anything caught up in all of these moving parts. But this is going to be a lot more interesting this way, so let's do it this way. Alright, so let's turn it on. We'll start off with 100 hectopascals here, and I'll press to turn it on. So I've got this little airspeed sensor here. Hopefully that will give you an idea of the speed control. If I can get it on the screen there somehow. Alright. I'll try and hold it in the same spot. So 6. And you go to 200. 8.4. And that's such little air that it's not even moving the needle. It's actually measuring at 1 hectopascal. So on these low rates, it's a little bit slow to respond. This is because of the way the PID controller works, but it eventually catches up and gets there. For the anything above around about 40 or 50, it gets there pretty quickly. So they're 8 hectopascals, and we're getting about a meter per second there. You go straight to 50, you'll see it catches up pretty quickly at these rates. And I like this little graph display because it's sort of pretty cool to see how the air pressure is responding. You can see it's sort of overshooting and coming back. But in reality, I'm actually really only using the number display, which is the same thing. It just shows it numerically, so it shows the setting value and the current value. And because of a lack of memory in the controller that I'm using, I'll probably end up dumping this graphic display because I won't have enough memory capacity in there or programming capacity in there to write the program for the remote interface. So it's a bit sad, but this probably will have to go away, and I'll end up probably just having this. Yeah, so it's pretty fun to play with, but you get the idea. It works really, really well. It's actually surprising how well it works. So I've already been using this for a little while in active service, and putting aside my natural personal bias, I actually really, really like this, and I'm entirely surprised that it works as well as what it does. And I'm just so happy to finally know exactly what air pressure I'm using for a given operation. I'm also happy to finally have access to those super low air pressure levels, just enough to keep the smoke out of the nozzle. And I'm in turn so happy that my air compressor is now working about 80% less than it used to. And of course, that's helping to maintain the workshop serenity, the most important thing. And I even have a plan in the work to link this directly to my CNC's GRB controller. which will not only allow me to set the required air pressure level and switch it on and off as a part of the G-code sequence, but it will also allow me to dynamically adjust the air assist levels throughout a given job. And I think that's really going to be quite useful, say for example for clearing pads where only really some of those smaller pads who need super high levels of air pressure to keep them cool. Well, there you go. That's it for this video. I hope it was useful to someone. And whatever you do, keep your fingers as far away from the subscribe or like buttons as possible. Please. I know it might be tempting, but just don't do it. Anyway, thanks for watching, and I hope to catch you in the next one. So, I'll see you then.